Welcome everyone to the second edition of the WAS seminars. So we're very happy to have Josh Kirklin with us, who's a postdoc at Perimeter. He did his PhD in Cambridge under Malcolm Perry and was then a postdoc in Okinawa. And he will tell us about black hole singularities and quantum reference frames. So stage is yours.
Okay, great. Thank you very much for inviting me to talk at this seminar. It's a great honor to be only the second, and I'm pretty excited about what WAST will achieve. So I'm just going to talk about black holes, singularities, and quantum reference frames. So here's a plan for the talk. So I'm going to spend just a little bit of time reviewing some stuff that we're mostly familiar with, I think. So I'll start with looking at classical gravity, which has some very strong rigid structures that constrain the dynamics of areas of surfaces. So these include the area theorem, the focusing, and singularity formation. Then I'll go on to how these things are corrected in semiclassical gravity. So these are all upgraded to semiclassical counterparts. But then the bulk of the talk will be about upgrading this again and going beyond semi-classical gravity by now incorporating quantum reference frames. And so what these do is they relax the assumption of classical time, which is part of semi-classical gravity, and this gives you significant modifications to these rigid semi-classical structures, which I think have a lot of very interesting consequences. Um, yeah. Okay, so yeah, let me start with the classical picture. So in gravity, the area of some surface, the equation which governs the evolution of that area, uh, is the Raychaudhuri equation, which it takes this form. So here you have, I'm imagining you have some codimension 2 surface with a certain area. We shoot out some null light rays from that surface, and this sweeps out a null surface in space-time. And then we want to imagine, we want to think about how the area of that surface evolves over the null evolution. And so here V is some null affine coordinate along the surface, and that's the thing we want to measure the evolution with respect to. Theta is the expansion, so it tells us how the area changes over that time. And then these other terms, sigma squared and the stress tensor, these represent the radiation that goes through the surface. And so using this equation, we can determine how the area will evolve according to the radiation that traverses it. And a very important extra ingredient here is the null energy condition, which is typically assumed to hold in classical gravity. And that says that this component of the stress tensor along the null surface is non-negative. And so overall, this means that the right-hand side of this equation is a negative quantity. And so you can immediately conclude that this derivative of the expansion or the second derivative of the area is a negative quantity. So that is focusing, when radiation goes through the surface, it causes the surface to bend inwards. And focusing itself is physically interesting, but it also implies some very rigid things. So, for example, the area theorem follows from focusing. So the area theorem says that if you have a black hole horizon, then the area at some later time has to be greater than the area at the early time. And this is implied by focusing because a horizon is defined by having vanishing expansion in the future. So if you just integrate back this focusing equation, you find that the expansion has to be positive. And the other very strong implication of focusing is the formation of singularities, which a very simple version of that argument is if you ever get to a point where the expansion is negative, then by integrating this equation, you find that the expansion will diverge to minus infinity in a finite affine time. And if you if you do this, more rigorously and more carefully about expansions in both null directions and so on, and you use some global assumptions, then this is really the basis of the Hawking-Penrose theorems that tell you that singularities will form generically. Okay, so that's my one slide on the classical setup. So how do we go to the semi-classical picture? Well, we have to correct this. And the first inroad here was in, in the 70s, that this discovery of the area theorem and the other laws of black hole mechanics resembling laws of thermodynamics, as well as the discovery of Hawking radiation. Well, this led Bekenstein and Hawking to suggest that the black hole entropy is actually proportional to the area with a certain factor. But there's a little bit of inconsistency here. And well, when I just argued for the area theorem that it increases over time, what I used was the null energy condition. But actually, Hawking radiation and other effects in the quantum theory, they don't obey the null energy condition. For example, Hawking radiation accounts for a negative energy flux at the horizon, which is violating that null energy condition. So really, in the presence of those quantum effects, the area doesn't have to increase; it will decrease. But Bekenstein made a very nice guess, which was, okay, maybe the area can decrease, but he knew that the entropy of the fields outside had to increase in some way because of the Hawking radiation. So maybe if you just add these things together, then you'll get a quantity which would still increase. And that's the generalized entropy. And I think a modern understanding of generalized entropy is that it's really a renormalized entanglement entropy. So this was a viewpoint put forward by Susskind and Uglum and others, which is that each of these two terms, the area term and the field entropy term, these are UV divergent quantities, but their combination, somehow those divergences account for each other. And this thing is better defined than the individual terms. So now, if generalized entropy replaces the area in the semi-classical theory, then instead of the area theorem, what we now have is that the generalized entropy is the thing which is always increasing. And so this is the generalized second law. So thermodynamics with black holes in semi-classical gravity. So just to make clear what this implies is that, okay, now we're in semi-classical gravity, the black hole can Hawking radiate, so it can evaporate, its area has to decrease at some point. But what this generalized second law is saying is that the generalized entropy still increases over the course of that evolution. And so Bekenstein made this guess, but it turns out to be much better than just a good guess. So you can actually prove this to quite a good degree of rigor. And I think the nicest, most powerful proof was due to Aaron Wall in 2011. And rather than just using, it's really a very quantum information style of proof. It's not a very geometric kind of proof. The ingredients, they're a combination, I suppose. And the way it works is like this. So you take this horizon, you want to compute the entropy outside of that horizon at a certain time, and so the time gives you a cut of the horizon, so like a space-like slice of the horizon. And outside of that cut, there's a certain algebra of observables. So this contains operators acting on all of the fields outside of that cut of the horizon. And now you can say, okay, I have two different times. Um, there are two different cuts of the horizon, and there are two different algebras of observables outside of those cuts. And because any observable at the inside of the later region is also inside of the earlier region, these algebras obey this inclusion. And now there's a very general result in quantum information theory, known as the monotonicity of relative entropy. It's also sometimes called the data processing inequality. And what Aaron Wall did was just to apply this inequality to this situation. Um, there was an extra step he had to do now, which was to impose an ultraviolet cutoff on the fields. And the reason he had to do that is because, as I said, these two terms in the generalized entropy are ultraviolet divergent, and so he had to do this in order to get control. And well, he also had to use that the modular Hamiltonian of the vacuum is proportional to the area. These are just words, but I'm just trying to give you an overview of the sketch of the proof. But really the point is that this monotonicity is what implies the generalized second law. So you compute the relative entropy with respect to the vacuum, which is thermal in some way, and you find that you get this monotonicity of generalized entropy. And so the key points here are we have an algebraic inclusion and we have monotonicity of relative entropy. And I want you to remember that because later on I'm going to generalize this proof to include quantum reference frames. Okay, so the GSL is what replaces the area theorem. And we can equally well ask what replaces this focusing and the formation of singularities. So if the null energy condition is violated in semiclassical gravity, then we can't use the classical singularity theorem because the classical singularity theorem depends on energy conditions. So, but maybe in semiclassical gravity we can get something that replaces that classical focusing theorem. And so, as we've seen in the GSL, it seems to be a good idea to replace the area by the generalized entropy. So we can just do another guess, which is just to take the ordinary classical focusing inequality and replace the area by the generalized entropy. And this is what's known as the quantum focusing conjecture. I've written this very schematically. It's more complicated than that in reality, but just to get the point across. And so we can use this quantum focusing conjecture. It turns out if we assume that it's true, we can generalize the classical singularity theorems to what are sometimes called quantum singularity theorems. And to be clear, it's not that the singularity is quantum in some way. It's just that in the quantum theory, we still run into singularities generically. Even with the absence of the null energy condition, by replacing the area by the generalized entropy, we somehow capture the quantum corrections. And now I showed you this proof by Aaron Wall of the GSL. I think it's fair to say that the QRC is not proved as rigorously as the GSL. It's much closer to a conjecture at this point. It's possible to prove a restricted version of it in some specific models of gravity. But what you can do is you can take a certain perturbative limit of the quantum focusing conjecture. And then what you recover is something called the quantum null energy condition, and you can prove this more generally using some very nice algebraic QFT techniques that I don't have time to go into. So just to summarize this first part of the talk, so by considering the dynamics of the areas of surface in classical gravity, we find these very rigid structures. So the area increase of the area theorem, the generic formation of singularities, and even in semi-classical gravity, these rigid structures seem to be upheld because we just have to replace these things by the GSL and the QFC, and the structures are upheld by mixing together geometry and quantum information in a very interesting way. And this is all a very nice story, uh, but there's a problem, and we're all familiar with it, which is the information problem. Um, so just there are many different versions of the information problem, of course. I just have one version of it that I'll put here, which is that if you start in a pure state so that the entropy is zero, then you let a black hole form and then evaporate. Well, the area of the black hole is zero before and after this process. And so the entropy of the outside before has to be zero, but by the GSL, the entropy of the outside after has to be non-zero. And so this would seem to imply that pure state has turned into a mixed state. So unless one of these previous assumptions that I've loosely described fails, then one possibility that one thing you can conclude is that black holes would lose information. Of course, there are lots of ways you can argue against this, and I'm going to present one in the rest of the talk. So how could a more full theory of quantum gravity argue against this information loss? Okay, so I've drawn the energy scale here, and I've put this marker where the Planck scale is. And well, we know that semi-classical gravity should be something that applies below the Planck scale. So we've so far stayed in this regime. And so maybe we can look to the ultraviolet to resolve this problem. So what would that involve? We'd have to do some modification of the micro physics. We could do this with loops or with strings or maybe many other things. And it seems to me this will be a very model dependent approach. Okay, there's actually another scale that I haven't drawn yet. There's an IR scale, and the semi-classical regime is also above this IR scale. And the IR scale isn't quite as universal as the Planck scale. It will depend on the context of whatever physical system we're considering. So it could be like a characteristic length scale of the system. And actually, semi-classical gravity has to stay above this length scale. And the reason for that is that when we do semi-classical gravity, we're making some assumption that the reference coordinates, the reference degrees of freedom that we're using behave classically. So if we want to maybe try and look for a resolution down at this infrared end of the energy scales, then we have to account for quantum reference frames. And so why is this an infrared issue? Well, if we're deep in the IR, then that means that we have small energy fluctuations, and that means that we have very large time fluctuations. And so anything that we are trying to think of as local in time doesn't quite make sense anymore. Things will delocalize, and this will happen in space as well. And unlike the UV end of the scale, this is a very universal thing. It's sort of driven by symmetries of gravity and principles of gravity. So it seems like if we look at this end, we don't have to make any big claims about the full theory of gravity. So in this talk, I want to look at the IR end. And so I said quantum reference frames. I should say what quantum reference frames are for anyone who is not familiar with that term. So um, one of the principles of gravity is general covariance, which says that we have to use reference frames such as coordinate systems to describe physical experiments and observations. But gravity is also background independent, so there are no background coordinate systems. There's no background notion of time. Uh, so whatever reference frames we use have to be built out of dynamical degrees of freedom, so clocks and rods. And in the quantum theory, those clocks and rods are made of quantum degrees of freedom, so they're actually quantum clocks and rods. And then people don't say dynamical, they just leave that out and call these quantum reference frames. And now there isn't really a choice here. I want to emphasize that what I'm going to describe in the rest of the talk is not a trick. Um, Diffeomorphism invariance means that we have to use quantum reference frames in quantum gravity to describe local observables. And semi-classical computations really, they typically just neglect the quantum reference frames. And so this is the weak point in the semi-classical arguments that I want to attack. Um, and just to say a bit more on why quantum reference frames capture this non-trivial infrared structure. So if we have a quantum clock, it has a certain energy, and moreover, its energy can fluctuate because it's a quantum object. And when its energy fluctuations are much larger than this IR scale, then what that means is that the quantum clock has a very sharply peaked time reading. And so we can really treat it as if it's a classical clock. So I put much less than one here, but really it's much less than the representative scale of the system that we're using the clock to measure. And if the clock behaves classically, then really these semi-classical statements, this GSL and QFC, that's when they actually make sense, because in these statements we're treating this time parameter t as a classical object. But if the energy fluctuations of the clock are much lower than the Planck's or lower than the IR scale or comparable to it, then the fluctuations of the time read by the clock are no longer negligible. They become very, very important. The degrees of freedom delocalize in time relative to the characteristic length of the problem. And so the rest of the talk is to account for this and to look at the consequences for entropy and singularities and so on. And so I'm going to involve two clocks. So one will be a boost clock. So there's this region outside the horizon, and you can consider a boost within that region. And the other one will be a null clock. So it will, whereas the boost clock measures time along the boost, the null clock measures time along some null translation along the horizon. And both of these clocks are very important in this story, it turns out. So the boost clock, its role is to sort of give a reference energy scale and to be associated with the thermal nature of the fields outside the horizon. While the null clock is determining the time at which we compute the entropy. So obviously we need to have a time at which we compute the entropy in order to consider the way in which that entropy evolves over time. And so the boost clock, one amazing thing that it does is it regularizes the entropy of the fields. So if we take some algebra of field operators in some subregion, um, well, you typically find that the fields in that subregion in the vacuum are thermal with respect to a boost inside of that subregion. And moreover, the generator of the boost is in perturbative gravity is and believed to be beyond perturbative gravity is proportional to the area of the boundary of this region. And so now if you put one of these boost clocks into the region, and rather than just considering the algebra of field operators, you consider the algebra of observables for both the fields and the clock, then even though the entropy of the fields is a UV divergent quantity, um, uh, this is due to infinite entanglement near the boundary of the region. It turns out that the entropy of the fields plus the clock is a finite quantity. Um, and so we don't need to put a UV cutoff in by hand, which is very nice in gravity because that's sort of difficult. And the null clock, okay, the boost clock regularizes the entropy. The null clock tells us where we're computing the entropy. So previously, I was thinking of these times at which I compute the entropy as fixed with respect to some classical time coordinate, but now I want to make them out of dynamical degrees of freedom. And one way you can do this is you can imagine that there's a particle falling in and it crosses the horizon at a certain point, and that's what defines the location of that cut. And this is a gauge invariant definition of that time. So the region outside of that cut is sort of a well-defined physical subsystem. And actually, there are many ways to construct these dynamical cuts. You don't have to imagine particles falling in. You can think maybe like I put this cut where a certain field has a certain value, or any other way you like. And the same is true of the boost clock. So for these clocks, we can sort of use any degrees of freedom that we would like. And it's fair to say that the situation is best understood for very simple quantum mechanical clocks, um, which have a very, the simple L2 of R Hilbert space. But ultimately, we should, uh, use the fields themselves to measure time. And then you have to be very careful about how you control the quantization and the anomalies that might arise. And you can see these papers, this one coming out hopefully very soon, about how you can do that on null surfaces. But in any case, the point is that the core structure here is the same, regardless of how you come up with this clock. The mathematical structure is that we want to describe this subsystem relative to a quantum reference frame, and the correct way to do that is to use what's called the cross product algebra. So the cross product algebra is the algebra of operators for a system relative to a quantum reference frame. And it has this notation. What it really means is that it consists of dressed observables and reorientations. So this G is a group that corresponds to the symmetries of the QRF. And so what is a dressed observable? Well, you take your QRF, it gives you a point in space-time, and you measure the field at that point. And that's what's known as a dressed observable. And what is a reorientation? Well, you can leave all of the fields alone, but just change the state of the QRF. So, change the time of the clock. And so cross product it sounds mathematical and mysterious, but that's all it really is. We have these dressed observables and reorientations. And a very important point that I should say is that in the semiclassical theory, this generalized entropy is a little bit mysterious. It mixes geometry and quantum information, and it has nice properties, but it's a little mysterious where it came from. But once we include QRFs, it's no longer mysterious. Generalized entropy is just the von Neumann entropy of a system relative to a QRF.
Josh, 10 minutes.
Thank you. Okay, so I'm describing a system relative to a QRF. So at the moment, I'm outside of the semi-classical regime, but we want to be able to compare this setup to what we already know from the semi-classical regime. So how can we recover the semi-classical regime? Well, we want the time of the clock to be very sharply peaked so that it behaves classically. And this happens when the energy fluctuations of the clock are very large relative to the energy fluctuations of the fields. So in this case, this IR scale is set by those field energy fluctuations. And what's very nice is that if you're in a state which satisfies this this inequality, the von Neumann entropy that you would compute for this cross product algebra, so this algebra of fields plus QRFs, is exactly equal at leading order to the semi-classical generalized entropy. So it has the area term and it has the entropy of the fields outside. And then there are some corrections which come in powers of the ratio of these energy fluctuations. And these corrections are dependent on the QRF that you use. So these are observer-dependent corrections to the gravitational entropy. They go away in the semi-classical limit, but they're there outside of the semi-classical limit. And so this area plus S out, this is the definition of generalized entropy in the semi-classical theory. But this setup now tells us how we should define generalized entropy beyond the semi-classical regime. We should just set that the generalized entropy is equal to the von Neumann entropy of the fields plus the QRF. We need to have some way of extending this definition beyond the semi-classical regime. The semi-classical definition doesn't really make sense because it depends on classical localization. And this is a very, I would say, extremely natural extension of the definition. Okay, so armed with this, I wanted to first say that if we're defining generalized entropy beyond the semi-classical regime in this way, then something we can immediately conclude, is that this is a fine-grained measure. So one way we could have gotten out of the information problem as I expressed it before is that the semi-classical generalized entropy could be a coarse-grained entropy. So coarse-grained entropies are entropies that you associate with not being able to do arbitrary measurements inside of a system. So this includes thermodynamic entropies or low complexity entropies. And these things, coarse-grained entropies, don't need to be consistent with, they don't need to decrease in order to be compatible with unitarity. They can increase over the evolution of the system, and you can still have a unitary evolution. But now that we're including QRFs and we see that this generalized entropy is just a von Neumann entropy, this means that it is a fine-grained entropy, so there's no ambiguity here. And so now it may be even more desirable to try and restore unitarity. So to do that, we need to look at how the GSL might change in the presence of QRFs. And as I mentioned earlier, I'm going to just use Aaron Wolf's argument, but put QRFs in and see what changes. So we now have a dynamical cut, which tells us a time along the horizon. So that's given to us by some clock, some red clock, null clock. And we also have a clock for the boost inside of the region. And there's this associated algebra of observables of the fields plus the quantum reference frames, which is a cross product. Uh, but I'll just write it like this. And so you can take two of these algebras, one to the future of the other. We have that one is a subalgebra of the other. I think I have this inclusion the wrong way around, but the later one is a subalgebra of the earlier one. And so now we just apply this monotonicity of relative entropy. We don't need to impose a UV cutoff, unlike Wall's original proof, because the QRFs do the regularization. And skipping all the details, what we find is this. So the terms on the left, that would be the usual GSL, but the QRFs give this red correction term, which you can think of as the free energy of the QRFs.
Josh, sorry, you have about 5
Yeah,
minutes.
5 minutes. Okay, thank you. So this fundamentally modifies the second law. So to give a bit more detail, this free energy term, it's the energy of the reference frames minus their entropy. And here I'm in units where the Hawking temperature of the black hole is equal to 1. And so the key term here is this entropy term, and it comes with a minus sign. And the quantum reference frame entropy can be arbitrarily positive, which means that we can satisfy this inequality while having this generalized entropy decrease. So previously, in the semiclassical gravity, this curve of generalized entropy was always increasing over time. But now, due to this QRF correction, it's allowed to bend back down to 0. And so the information problem, as I posted before, is it doesn't really apply anymore, because there's no constraint here that says that the entropy after has to be greater than the entropy before. Now, what would we have to sacrifice in order to get this entropy going to 0? Well, we would need this free energy term to become a large correction rather than just some small effect. So the entropy of the quantum reference frames would have to grow very large by the endpoint of the evaporation. And there's a natural candidate for what it would become, for the reason why it would become large, and that would be that it becomes entangled with sort of the Hawking radiation in some way. But this is speculative. And just to be clear, the usual semiclassical GSL, this includes that GSL. So you can recover that usual case by going to a semiclassical regime in which you treat the reference frames as classical. But outside of that regime, you can violate this to an arbitrary degree. And there's a simple example. You can put the fields in the vacuum state, and then you can just ignore them. But you can entangle all of the QRFs with each other, and then this difference in generalized entropy is defined beyond the semiclassical regime as a von Neumann entropy of a crust product algebra. Can take any value you want, really. So you can violate this to an arbitrary degree. So what about quantum focusing? Well, this is the semiclassical QFC, and one way to state it is that you need this log of generalized entropy to be convex as a function of time. So what we can do in the QRF setting is we can take three of these dynamical cuts now, um, and we can consider what it would take for convexity to be obeyed. So it's basically this inequality that I've written down. But just like the GSL, we can find states in which the two sides of this inequality, take arbitrary values by entangling the QRFs in the appropriate way. So uh, just like the GSL, by entangling the QRFs, we can avoid this quantum focusing. Yeah, so again, this fundamentally changes the picture beyond the semiclassical regime. And so if the QFC can be violated, it's very natural to ask what happens to singularities. Um, and I don't want to claim that this means that singularities won't occur. They definitely will occur. Um, but but what we can say is that by accounting for QRFs, it may be possible to avoid some singularities. Um, and this comes at a cost. Um, as long as we assume that the QFC holds in the semi-classical regime, in order to violate the QFC, we have to leave the semi-classical regime. So whatever quantum reference frames we're using have to fluctuate a very large amount. And so, I mean, yeah, this is it's a very imprecise thing, but it's kind of fun. It's kind of a quantum relational version of cosmic censorship where, you can resolve these singularities, but wherever that occurs, it has to be in some region of space-time which you could only possibly probe by using a very highly fluctuating quantum reference frame. So, these singularities are hidden in non-semiclassical regions of space-time. Um, okay, so to wrap up, classical and semi-classical gravity, they have these very rigid structures, but incorporating QRFs allow us to bend these rules. They let us identify what generalized entropy is. It's the von Neumann entropy of a system relative to QRFs. When these QRFs behave non-semiclassically, then the rigid structures break down, and this fundamentally changes uh, a lot of interesting things. So it alters one of the premises of black hole information. You don't necessarily have the GSL, so maybe that's a way to avoid information loss. And it gives potentially this new viewpoint on some uh, nature of space-time singularities. Their inevitability, as encoded by singularity theorems, is really depends on time remaining classical. And just to finish, so I had this flowchart at the very beginning of the talk. We're going from classical to semi-classical to gravity with QRFs. Of course, the next step, in some respects, is to go all the way to full quantum gravity. But what I want to try and encourage is that this maybe isn't necessary to get a lot of interesting stuff. So this gravity with QRFs, it's this intermediate step in between semi-classical and full quantum gravity. And whereas the full thing is very model dependent, strings, loops, whatever, uh, adding QRFs to gravity is very it's there's not a lot of choice there. There are universal principles which govern what we should do. And as I've described, it's rooted in IR physics, and that's well below the Planck scale. So that's more experimentally accessible than the UV full quantum gravity stuff. And hopefully I've convinced you that involving QRFs is already enough to provide new answers to these deep questions. And before ending, I have an announcement, which is this relativity reframe conference at PI if I've interested you with what I've talked about, then you should come to this conference. It'll be in October. Very recently learned that WAST is contributing some funding, so we're very grateful for that. And if you want to find more, there's a URL here. Okay, thank you very much.
Yeah, thank you very much for the beautiful talk. So, are there any questions? So, I see only clapping hands. Okay, so Madrid, I think, was the first to raise the hand. So let me hand over to Madrid. Can you unmute yourself? Or do I actually have to do that? No? I guess you should. Can you unmute yourself?
Mute?
Yeah, now it works. Yeah.
Yeah. Hello. Can you hear me?
Yeah.
Yes.
Yes. Hello, probably we should.
You just speak and it's coming to you. So, yeah.
Oh, sorry for the confusion. We have a new camera. Sorry. No.
So was there a question or was there not? Sorry,
I
Another question, and we'll come back later.
Oh, okay. So then,
Okay.
Daniele, maybe can you unmute yourself?
Yeah, so thanks for the talk, first of all. Super nice. So it seems, if I understand correctly, that the quantum aspects of the reference frame basically induce can be seen as introducing a form of non-locality in the framework, because a sort of space-time localization, and in particular the localization in time, becomes a sort of not sharp. And so first of all, I'm wondering if you can put some bounds from whatever source on how we are allowed to consider this, the reference frame non-sharp and still using it as a reference frame. Because I would imagine that beyond a certain threshold, whatever it is, it simply becomes a useless frame. And so, well, we can still use it, but it doesn't make too much sense to track space-time evolution. And the related question is, you're allowing the reference frame to be quantum, potentially very much quantum. At the same time, we are still approximating the picture as one in which the frame is still not dynamical, and so not fully physical. So I'm wondering, there should be an interplay between these two aspects. So a priori, I could imagine that in some of the situations you were discussing, neglecting the dynamical nature of the reference frame is also a very tricky approximation.
Okay. Yeah, thank you. So for the first question, so mathematically, there's no issue with defining these observables. Like you can dress observables relative to a clock, which is fluctuating a lot. You still get an operator that you can measure. What you say about the observable being kind of useless is kind of correct. If it fluctuates a significant amount, then you can't localize any measurements, and it becomes useless. And in a paper with Philip and Stefan Eccles and Julian de Voist, we investigated this in one of those sections. So this semi-classical regime, where the fluctuations of the clock energy are much greater than the fluctuations of the field energy, that's where the clock is useful. But you can look at what we call an anti-semi-classical regime, so where you turn this inequality the other way around. So the fluctuations of the energy of the clock are much lower than the fluctuations of the energy of the fields. Or conversely, the time of the clock is fluctuating a very huge amount. And so the observables are all smeared out in time, and what you find is that computing the entropy in that kind of regime, it's as if you didn't have the clock at all. So that's I don't know if I fully answer that question, but you can consider the situation mathematically and physically, and things tend to make sense. For the second question, when you say dynamical, just to clarify, uh, so these are dynamical objects, but they're not interacting within this approximation. Did you mean interacting?
Yeah.
Yeah. Okay. Yeah. So yeah, very good. That's yeah. That's something I think we need to understand better. So these reference frames are idealized in the sense that they're not interacting with the fields. Of course, there will be interaction terms, and presumably we're in a regime in which those interaction terms are very small. But they'll be, I think, they can be ultimately responsible for things where we maybe start off in a semi-classical regime with small fluctuations of the time, but due to those interactions, sort of the time starts to spread out, and so we leave the semi-classical regime, and that might be something that would be necessary for these kinds of resolutions to work, because you need to transfer, you need to go between the two regimes at some level. So I'd love to understand that better, but I don't have any concrete thing to say beyond that.
Thank you.
Thanks.
Yeah, there are actually some models where you can see that interactions ruin semi-classicality in the clock relational models. So I don't know if anything has changed in Madrid. Meanwhile, let me have. Oh, there has.
Yes, we're fine. We're controlling the camera. Thank you. Sorry for before.
Okay.
Josh, that was super interesting. I have, I had plenty of questions. I look forward for discussing all this more in detail with you. I'll just stick to a few. But let me premise with two comments. Your presentation of the previous stuff was absolutely brilliant and clean, and the idea that there is an infinite time scale which is relevant, it sounds completely right to me. That part of the story sounds right. It's there's a time scale issue here, and it seems you're putting your finger into a good point here. Now, what I don't understand, it's on some points you said. What I don't understand is what problem are you solving and what picture are you proposing, besides just saying, well, according to some people, the generalized second law give to generate a problem, and so since it can be violated, it might not be a problem. I don't understand the alternative scenario, and I don't understand. I would not say the generalized second law by itself generate a problem. So I was trying to focus in where exactly I missed you, and it's when you said the entropy so redefined is necessarily a fine-grained entropy. Why? I mean, I think I had a good understanding of generalized second law before your correction, which sounds very interesting, as something which is not a fine-grained entropy, and that seemed to me to be coherent with our own wall derivation, and that seemed to me to just be sufficient to avoid some of the problems that people bring in, which come in the moment in which you confuse the generalized second law with something that counts all the internal states. So why do you avoid the problem and you fall into a trap? From my perspective, am I missing something?
No, I think you're describing my point of view accurately. I think, yeah, it is definitely one way to get out of my argument without the QRFs. If you have a GSL interpreting the generalized entropy as a coarse-grained entropy, that's consistent with the unitary evolution. To some extent, I mean, I don't want to say too strongly. You could call it a cop-out, just putting everything in in stuff we don't know, stuff we can't measure.
No, wait. That's a jump. Why do you say so? That is a.
Well, I mean,
there's no,
it's sort of.
there's no problem until the black hole is a black hole. Then there's the end evaporation, and then we need a story of what happened next. So information is inside, and then there's a story of what happened next. If you want to say, I don't want to know what happened next because that's quantum gravity, that's fine. But then there's no problem. Where is it? Where's the problem? I just don't see it.
Okay. Well, so one thing I should say is I phrased the issue purely in terms of the entropy before the black hole and the entropy after the black hole.
Yes.
So and the inequality I wrote down, it was just an entropy for these perturbative fields before and a perturbative entropy for the perturbative fields after. So you didn't need to think about how the degrees of freedom were hidden in the black hole in order to have that statement.
Well,
I should say I'm not.
The remnant scenario, at the end of the evaporation, there's a long-term remnant. Information come out slowly, and entropy. So the overall thing is unitary, and information just goes in and comes out long after. The only problem comes if one assumes that the area part of the generalized entropy counts a number of degrees of freedom that are lost forever.
Right. Just to clarify, I'm not dogmatic about this. I'm not saying that what you're proposing is not true. I'm more of the point of view that, including QRFs means we don't even need to think about these questions. So to clarify, you asked before why I think of this as a fine-grained entropy. And the reason I think of it as a fine-grained entropy is because we have this entropy that we're writing down as a von Neumann entropy. So we can do arbitrarily complicated measurements of arbitrary order correlation functions of the fields before and after the black hole. And before and after the black hole, the algebra that we're considering, it's not a subsystem, it's everything outside of the black hole. So it is everything in the universe. And so there's really, unless you want to add in some very UV quantum gravity extra degrees of freedom that are hidden in some way, there's nowhere for that coarse graining to take place. And of course, I'm not saying that won't be something that happens in quantum gravity. I'm just saying within this picture, it doesn't have to happen. But like I said, I'm not.
But what is your picture? I'm still missing the picture. Is there a Planck? Is there a page curve? Or not?
Right. So
I don't see your proposal.
So you don't. Yeah, this doesn't derive a page curve. It just says that the generalized entropy can obey the page curve, and there's no issue with a GSL. So it's a loophole. It's not a derivation, but it's a loophole that you get by including QRFs.
So your free energy of the quantum reference system can become relevant already far before the quantum gravity regime. Is that what you're suggesting?
I think so. And so I don't have a full answer, but I think that maybe the best way to understand this in terms of these energy scales.
Yes.
And so this window somehow closes by the time you get to the page time or something like that. And this picture actually, it talks about the fluctuations of the reference frames, but it misses out the entanglement of the reference frames. So that's something that also affects the situation. Yeah, I would love to know more about this. My intuition is that as you evolve the black hole, at the beginning, this semi-classical window is very large, but as you approach the page time, the window closes, and entanglement between the reference frame and the Hawking radiation, for example, becomes non-negligible. But I don't really have, you know.
Okay.
I don't.
Okay.
Yeah.
Is that okay? You don't have a full picture.
Right. Yeah.
I have another question, but I don't want to monopolize too much. I see other people, so I'll stop here and I'll just ask another question if there's more time. Thank you.
Okay. Thank you.
Okay, then maybe next we have Czaslaw, and then we can come back to well, there's also Ali, and then maybe afterwards we come back to Madrid. Czaslaw.
Okay, so yeah, thanks, Josh, for the very nice talk. Really important. I feel this is really important what you're doing there. I have a question about your semi-classical limit. If I'm not mistaken, you identify this with sharp clock state. Like
Yes.
And this feels like just the opposite of what I feel. It's because the sharp, very sharp, I mean, literally sharp measurement of time will induce a huge back reaction on space-time because the energy, distribution will be very large, and therefore, the space-time around that clock will be very much non-classical. This is not what we, let's say, in the lab think about the classical clock. So usually when one goes in the semi-classical limit in quantum mechanics, one kind of overlooks this as well and use, for example, decoherence in position basis. But obviously it shouldn't be a very sharp position basis because immediately the system will explode in momentum. And the next time we measure position would not be anywhere where we expect this classically. So it's rather something which is a coherent state it is most classical state. So it's a coherent state in a phase space in which here will be like some minimal, let's say, wave packet in energy time that would maybe correspond to the classical. I don't know whether you want to comment on that.
I think I completely agree. Yeah, so I've written this semi-classical limit. Well, I've talked about it as a sharp clock, like you say, and I think this is related to Daniele's point that I'm ignoring interactions between the clock and the rest of the degrees of freedom. And if those interactions are there and it's like arbitrarily sharp, then I agree with you. These energy fluctuations will back react, and we have to take that. You have to put that under control. So I think in that situation, there's another relevant scale that maybe is related to the scales I've already talked about, but I'm not 100%, which is the scale of these interactions. So we want the clock to be very sharp, but not so sharp that its energy fluctuations give you like uncontrollable back reactions on the space-time. And I think as long as we assume that window exists, so that the clock is sharp enough to resolve the fields, but not so sharp that it destroys the space-time, then I think qualitatively we're safe. And I think the right way to describe that, yeah, for general kinds of quantum reference frames, I think coherent states is the right framework. I agree with that. I don't know if I've...
No, yeah. Thanks. I agree with what you said there. That's my understanding as well.
Okay. Thank you.
Okay. Ali, can you unmute yourself?
Yes, thank you. So first, thank you for the nice talk. And sorry, I'm at the airport. I may have missed something trying to catch my flight. But so I just wonder, is the main statement you're making, is it valid for certain reference frames? In that case, what do we do with the other reference frames, in your opinion? And then if it's valid for basically any reference frame, just what you're saying is that if you include a description of the quantum reference frame, then um, uh, then that then you can violate the bounds. Then what happens if I choose my reference frame to be like the most boring, closest possible to classical frame? And then either I recover the the paradox because I'm back to the classical case or semi-classical case, or if not, then how does it work?
Yeah, thank you. So there are two things I can say. One is that it's true that all of these arguments depend on which quantum reference frame you pick. So the entropies you measure and so on, that will depend on which reference frame you pick because that gives you a different algebra and a different entropy. The other thing to say, just in more detail, is that yeah, you're correct. You can say, let me try and pick the best quantum reference frame for the situation I'm interested in. So the one which gives me the closest possible thing to the semi-classical approximation. And that's something you can very well do. What I would disagree with is that best quantum reference frame will behave as a classical reference frame because the quantum reference frames you're allowed to use are defined by the degrees of freedom within the system, and there's no way to construct a perfect classical clock out of quantum degrees of freedom. So even if you choose the best possible clocks, you'll still get these corrections. And perhaps involving interactions means that even if you pick a clock which is good at some time, it becomes bad at another time. And yeah. So yeah, I don't know if that.
Yeah, thanks. Yes, thank you.
Okay. And I
Maybe
hope
just
you
a
catch
brief
your
follow-up
flight.
on this. Oh, sorry, did you want to say anything more?
I was just gonna say good luck with the catching the flight.
All right.
Thank you.
But I mean, basically, that relates to a question I had also from so what Ali was just asking is when it comes to singularity theorems or quantum corrections to it, presumably you wouldn't want to make the existence of a singularity dependent on which frame you use to probe it. So, I guess, I mean, as in our joint paper, the horizon entropies are anyway quantum reference frame independent if you include everything, and I guess that's also what you should have in the second law. So would a similar kind of argument hold here that basically the quantum focusing conjecture or whatever deviations you get when you use quantum reference frames, that whether or not you might have a singularity, that this shouldn't be a frame dependent statement.
Yeah, I'm not 100% sure. There is an operational perspective on this, which is that suppose we do try and do something that's QRF independent by saying let's pick the best QRF and let's try and observe the singularity with the best possible QRF that we have. Because we're going to the best one, this is a QRF independent statement because we're optimizing. But if that best QRF doesn't let us see the singularity very well, then operationally speaking, it's as if the singularity is there's no way to measure it. So I mean we can still indirectly measure it. It has consequences on the other degrees of freedom, but those consequences will be corrected in some way. I also wanted to comment that there's a more perhaps more direct argument for this kind of thing, which is again looking at these energy scales. And the point would be that if we have this singularity where the fields blow up and so they go to the Planck scale, but we want to resolve that singularity within some region of some small region of space-time, then this window will close because the IR scale is the scale of the singularity, and so the IR scale comes to meet the Planck scale, and so things inevitably become fuzzy. Yeah, I would love to explore these questions more properly. This is a sort of
Yeah, well, I think that would be very interesting. But maybe we should go on. So it seems Madrid has a question again. Is that Carlo or?
Just a general question, which always confuses me, Josh. You're a clear thinker. When you motivate the quantum reference system with general relativity, I heard this argument many times. I just don't get it because it seems that it's in the opposite direction. What happened because of general covariance is that if you look at the theory written in terms of coordinates, there seems to be a certain number of degrees of freedom. Because of general covariance, there are less. So what you want to do is to think that some of the apparent degrees of freedom are fake because the theory, the variables are just relational one degree of freedom with respect to the other. So one simple way of doing that in a physical readable way is to add a physical clock or a physical reference system and use it as a reference system, namely express the other field as a function of it. And then, of course, it does not have degrees of freedom. It does not fluctuate. So you just add it in order to recover all the previous degrees of freedom in spite of the gauge invariance, not so to add another degrees of freedom. So the quantum reference system that were born in the laboratory, thinking, okay, if I use an object as my reference system, that object is quantum mechanical, is perfectly coherent story. But the translation of that to general relativity does not work because of general covariance, precisely. So I get confused here. Why you want to take an algebra larger? Maybe you want to take an algebra larger, but then you have to divide by the gauge invariant, by the coordinate transformation. So then I don't know what are the degrees of freedom of the clock as opposite to the degrees of freedom of gravity. Do you see my confusion? I always hear this story and never get it.
Okay, I can try to answer. I don't know if I can give a perfect answer, but okay, so we can add a clock to the system.
Yeah.
So we can add this. It seems what you're describing is sort of an external clock that we're just adding on top. Yeah.
Fine.
Right. Yeah. So then we can sort of deparameterize that general covariance in that way, and I think I agree with you that by the Page Wooder's story, it's equivalent to just describing things in terms of the clock time in a certain way. I think I mean it's not very I want to do things not adding in these external clocks. I want to use the gravitational degrees of freedom themselves to define the clocks. And then those gravitational degrees of freedom will have quantum properties, and I don't know, if we want to compare readings in different clocks, then we have to if we want to compare pictures with respect to different clocks, then we have to take those quantum properties into account. I don't know if I have a perfect answer. I should say that the clocks that I'm considering here, I'm always implicitly assuming that they're made out of the gravitational degrees of freedom. Like, for example, in this work with Laurent Fidel that we're doing, we're using a particular very nice sort of field along the null surface, which is built out of the metric in a particular way, and it has very natural properties, and it's not something that we're adding externally. Yeah, sorry, I feel like I'm not addressing your question directly, but
Okay, I just wanted to voice this confusion that I have to the entire community.
But were you concerned about Carlo, about diffeomorphism invariance here or so? I mean, because the constraints are obeyed. I mean, these cross product algebras are gauge invariant. I mean, usually one should understand them to be invariant in a perturbative sense, at least in this sense. In this case, yeah, in a perturbative sense, you can make a sense of them as being invariant under perturbative diffeomorphisms. And then the boost constraint that defines these cross product algebras. I mean, that basically you're going to a boost invariant description. And so at the end of the day, the algebras are actually diffeomorphism invariant. It assumes implicitly that these algebras that you're already inputting into the cross product as a background, that they're already invariant under, for instance, linearized diffeomorphisms. So there are ways in which you can make sense of this as being diffeomorphism invariant. And then I suppose one thing about these clocks is that the hope is, and I guess that connects with what Josh was saying, that okay, some of these simple models that qualitatively what they capture, even though maybe you add it by hand to the theory, that qualitatively what it captures in terms of the UV regularization and so on, that this would also be captured by some dynamical field that already is included in your theory to begin with, where you don't really have to add it as a separate clock from the outside. And there are actually some such examples in this von Neumann algebra literature in recent years, where people used, for instance, some degrees of freedom coming from the inflaton or something like this in a cosmological setting, and then it still regularizes the entropies. So I don't know if that maybe.
I'm not sure there's anything wrong in that at all. I'm confused by the narrative that the fluctuations of the quantum fluctuations of the clock, because it is a reference system in the sense of generativity, which seems to me the opposite of what should happen. So whatever you do, whatever you want to consider as your clock degrees of freedom, whether it is part of the gravitational field or something else you add, it's in both cases. The precise point about picking up the gauge invariant part of the algebra is that it's the one where there are not degrees of freedom and quantum degrees of freedom and quantum fluctuations of the reference quantity.
Maybe I should, a good clarification here maybe is that it's true that the time of one clock is not a gauge invariant thing, so its fluctuations don't matter. But if we're comparing two systems, it's the difference between the systems which will fluctuate in a gauge invariant way, and that's really what is affecting all of these statements that I've described, where we're considering the differences in entropies, for example, between two systems.
Okay, that might be a track for following better. Yeah, I'm not implying that there's anything wrong. It's just a justification. The initial story. Oh, in quantum gravity, you need a physical reference system, and this is a quantum thing, and therefore that sounds wrong to relativists somehow. So I just might try to understand better the mathematics and sort of express it in a way that I might understand it better.
So actually, the clock fluctuation in terms of the energy, and these models are also gauge invariant. So they commute. I mean, the energy of the clock also commutes with a constraint in these models because it sits inside these non-interacting Hamiltonian constraints. Anyway, maybe we move on. So Julius?
Hey, yeah, thanks. Cool talk. I have a quick question. Towards the end, you suggested that kind of through QRFs, one might avoid some, but not all singularities. Could you say a bit more about that? Like, where do you think this could work? Where do you think this could not work?
Yeah, I can try. To be honest, I don't really know. That was more of a hedging statement. Well, I don't believe that this will resolve all singularities. I think that would require some kind of UV description to do. But I think yeah, the best I can say is this kind of cosmic censorship type of loose statement where if we were to have some kind of singularity that we could see with a classical reference frame, then it's very plausible that upgrading that classical reference frame to a quantum reference frame means we can't see that singularity anymore, at least within the same kind of mathematical, well, I want to say rigor, but you need to figure out what the theory of geodesically incomplete spacetimes means within this context. Yeah, I'd love to have something more precise to say, but yeah.
Okay. Yeah. Hi, Laurent. Can you unmute yourself?
Hi, everyone. I'm in a noisy environment, so I hope you can hear me well. I just wanted maybe to comment on or say something that answers the question, I think, of Daniele and Carlo and other people, Ali too. So maybe because it's about a work that's coming up. So what we're doing right now with Josh is that in the gravitational system, let's say for the Norway, I think there's a very definite proposal for what is the best clock possible. It's called the dressing time. And this dressing time has the property that it minimizes, so it minimizes the interaction between the clock and the system. So it really, in some sense, it's a proper definition along Norway of what you would call the Newtonian potential. And then you can prove, it's also such that, when you use this clock, the flux of energy is as positive as you can say. So in fact, it has many properties that defines it as the best clock possible. And what you can show then is that this clock, it is really, Carlo, about gauge invariant observable. Of course, what you're doing is you're measuring the quantum field theory degrees of freedom and radiation with respect to this Newtonian field, which you call the dressing time. And in the end, yes, these observable are less, they're less in the field theory. But then you can compare the fluctuation of this observable, the gauge invariant observable, the dressed observable, compared to the fluctuations of the naive quantum field theory observable. And you find that the fluctuation of this dressed observable is much bigger because this clock, this dressing time, which you can think as a null, Newtonian potential, if you want, has fundamental irreducible quantum fluctuation, which are minimized. So I think that answers, and to answer Daniel's question, this is a dynamical field. It's a field which is part of the gravitational field. So there's a very precise way for the null ray in which is the best clock you can identify. And then what Josh is saying goes through. What Josh here talked about is some external clock, which might be very arbitrary, but in gravity has the beauty, that it can tell you which one is kind of the best choice. So I hope that answers the questions. Okay, maybe more based on some upcoming work, and maybe Josh can comment.
No, I agree.
Okay, there's a thumbs up from Madrid. Yeah, thanks for the comments, Laurent. Are there any other questions? Okay, that does not seem to be the case. I guess we're anyway near the 1.5 hour mark. So then, yeah, let's thank Josh again for this very nice talk. And also thanks everyone for the discussion and staying on. And then I guess next month we'll have another edition of the seminar series in March. And okay, until then, goodbye, everyone. Cheers. Bye-bye.
Thank you very much. Come to our conference.